In the last lecture, we started with geometrical optics, and we found that as long as the aperture through which the light has to pass is much larger than the wavelength of light, then light can be treated as travelling in straight lines, and these straight lines through which light travels, they are called rays. Then we dealt with laws of reflection and refraction, and we found that they are valid on any surface. Surface may be round, surface may be plane, whatever the nature of surface, these laws are valid. Then we found when the surface is not regular, for example, this surface is not very regular, then the light falling on it gets reflected in many ways. It is called diffused reflection. The laws of reflection are valid at each point, but since these points are not regular, the reflection is called diffused reflection. And towards the end of the lecture, we found that if an object is placed underwater, then its apparent depth, the depth at which we see from outside, is smaller than its actual depth. And we start with one of the examples. A person underwater sees the sun at an apparent angle. Apparent angle is the one that the person sees at an angle of 30 degrees from the vertical. What is the actual direction of the sun in degrees from the vertical? The light is going to suffer refraction as it enters water. So, I have tried to show the actual direction of the sun and then the bent ray which reaches the person. It is very simple. If the actual direction of the sun from the vertical is I, then sin I by sin r is 1.33, the refractive index of water, and for the given value of r is 30 degrees, we can calculate what I would be, and if you calculate, you will find I is equal to roughly 42 degrees. So, the sun rays are coming at an angle of 42 degrees to the vertical, but because of refraction, the person inside water sees the rays coming at an angle of 30 degrees. You also know that white light consists of several colors, 7 prominent colors, and these colors are actually different wavelengths. So, the refractive index of glass or any other medium is different for different wavelengths, and since the refractive index is different, the velocity of light through these media of different wavelengths is also different. Look at this table. This table has the color red, yellow, green, blue and violet, wavelength 640 nanometers, 589, 509 etc., and this is the index of refraction. You can see that the index of refraction increases as we go from red to violet. Here is in greater details. We have got again the same thing, but we have got additional thing, frequency, and we also got the additional thing, the velocity of light for that color. And you see that as the refractive index increases, the velocity of light decreases from red to violet. And what is the effect of this? That when a ray enters, say 2 rays, one of blue color and one of red color, when they enter, they do not go parallel, because they bend to different extents. Red bends less than the blue, not the other way around, and they do not bend like this because the refractive index is not negative. So, if you have 2 rays coming like this, 2 different colors, then the red color will diffract less and the blue color will bend more. I have shown clearly here. White light enters this slab and you can see the colors separate, and the red is the least refracted and violet is the maximum refracted. And after they come out, they are all parallel, very narrow beam, and they all again in our eyes they mix up and we see that as white light. However, we shall see that if instead of a slab we have prism, then the colors will separate. Example 2. If white light is incident normally on a glass slab, which color will emerge first? You see, that the light is entering normally, that means the angle of refraction is 0 for both for all the colors in fact in the white light. However, they travel with different speeds through glass, and we have seen that the speed of red is maximum. Therefore, the red color will come out first. I was talking of a prism. Let us see this slab. This is a slab which is in the shape of a trapezium. Here the light enters, this OP is the angle of incidence, and this gets refracted to PQ, and this gets further when it comes out refracted as QR. Now, you can see that QR is no longer parallel to OP, which we found earlier. In the case of a slab, when the light comes out, the incident ray and the emergent rays, they are parallel, but not in the case of a slab like this. And what happens? That the angle between the incident ray and the emergent ray is this angle d. This angle is called the angle of deviation. And now I have got the complete prism. I had deliberately taken out this corner angle A. Why? Just to show you that even if the prism is not complete, the process of refraction through the prism is not affected, and it is exactly the same picture, except that I have added this corner here. So, you see this ray OP gets refracted, becomes PQ, and gets further refracted, becomes QR, and this angle D is the angle of deviation, which is the angle between the incident ray and the emergent ray. If we start increasing the angle of incidence from a small value, then that the angle of deviation starts decreasing, becomes or assumes a minimum value, and then starts increasing again. This angle is called the angle of minimum deviation. Why is it important? One of the importance of this minimum angle of deviation is in the formation of rainbow. What happens is the following: suppose this is a drop of water, and parallel rays from the sun are incident on this drop. So, what has happened? As it goes through refraction and then reflection from inside the water drop, the rays get out in this fashion, and you can see some rays are bunched, and this bunching is near the angle of minimum deviation. So, that is the importance. These rays are called rainbow rays. So, here again the same drop, we have got white light which goes inside, gets broken into different colors. I have shown the extreme ones, the blue and the red, and this is the angle of minimum deviation. This is the incident ray, this is the emergent ray after reflection through the water, and you can see this angle is about 42 degrees for red and 40 degrees for blue. These are the angles of minimum deviation for these colors when the refraction takes place through water. And it is at these angles that the rays that enter the drop, they are bunched and they give rise to the rainbow, and these rays are called rainbow rays. Same thing again, you see this is the ring that you see in the sky, and what is happening is that light is coming from the sun and it gets deviated through an angle of 42 degrees, and at this angle we see the rainbow. So, when we are standing like this, sun is at our back and we have water droplets in the atmosphere. At an angle of about 42 degrees we see the rainbow. Such a rainbow is called the primary rainbow. The arrangement of colors is blue is at a smaller angle and the red is at a larger angle. So, the red is outside. Now, it also can happen that the rays that enter not one, but two reflections inside the water droplet, and when they come out the colors are reversed, and I will show you an example. You can see one rainbow here in which the blue is inside, and if you look it more carefully you can see a very faint second rainbow which is a secondary rainbow, and which the arrangement of colors is reversed. Now, having done with this refraction through water droplets, giving rise to rainbow. You know, the important thing to remember is this: the rainbow can occur only when the sun is behind you and the atmosphere or the water droplets are in front of you. So, the rays come, they strike the water droplets, get refracted, get reflected once or twice depending upon whether the rainbow is primary or secondary, and if it is primary, then rainbow rays come to you at an angle of about 42 degrees. So, you see in the sky an arc with a radius of, angular radius of 42 degrees. We do not see the full circular rainbow on the earth, because the earth gets between the rainbow, so that we have only a partial rainbow. But if you are traveling in an aeroplane, for example, then you will see the complete circle of rainbow. Let us keep continuing looking at refraction at curved surfaces, and remember this: the laws of refraction remain valid, whether the surface is plane or curved does not matter. So, let us see a ray coming and entering this sphere. You see, this gets refracted inside this. This is the normal. You see, all radii are normal to the sphere. Therefore, this is normal, this is angle of incidence, this is angle of refraction, and when it comes out, this ray gets further deviated from the original ray and it goes like this. Take another ray, this again undergoes refraction, and you can see these two rays, the emergent rays, they meet at this point. That means, this sphere of say glass or whatever is acting like a device which converges these parallel rays to this point. Take another example. We have this ray O from O, and the normal is from the center. Obviously, the radius is normal, and therefore, this gets refracted, and since the air is outside, the angle of refraction is larger than angle of incidence, and the ray seems to be coming from the point I. We may say that I is the image of O, because the ray seems to be coming, if you see from outside, they seem to be coming from I. Let us look at now reflection from curved surfaces. The rules governing reflection remain the same, the laws of refraction are valid, and this is the spherical surface. Let us say this is a complete sphere, I am taking only a part of this. All radii from the center to the sphere are normal, and P is the geometrical center of this surface, and the radius of this spherical surface, of which this is just a part, is called the radius of curvature of this surface. So, we have radius of curvature of this surface, and we have this point which is the geometrical center of this reflecting part of the sphere. I am showing that again, all these are normals, and this is the geometrical center of this reflecting surface, and this diameter is called the principal axis. This joins point P with the center of curvature, and this is the radius of curvature, and all distances will be measured from P, which is the pole called pole of the mirror. This will be the reflecting mirror, this will be called the pole of the mirror. Now, to understand and to solve the problems of reflection and refraction from spherical surfaces, we need a convention. We need to give the sign to the various quantities, and if we use one convention consistently, then we will get consistent answers. And the simplest of these conventions is known as Cartesian convention. Why is it simplest? Because it is dependent on Cartesian frame. You are familiar with this x axis, y axis, this is a Cartesian frame, and you also know that quantities along this x axis are positive, along this negative x axis they are negative, upward along the y axis they are positive, and downward along the y axis they are negative. So, we shall use this Cartesian frame to base our sign convention. And here same convention is depicted, but with the provision that the direction of light is this. We always assume the light to come from the left. For using this convention, we always assume the light to come from the left. If the light comes from left, then distances are measured from the point P. So, all distances in this direction are negative, all distances in this direction are positive, all distances above the axis in this direction they are positive, all the distances measured downward from the axis are negative. So, this is the convention. Again I repeat, now this is the reflecting surface, the light is coming from the left, this is the assumption we always have to make, light is coming from the left, and from the point P we measured all distances. Distances measured on this side are positive, distances measured on this side are negative. Distances measured upward from the axis are positive and downward from the axis are negative. There is usually a confusion regarding this direction of light. You see, in a lab or anywhere, for example, I am sitting here, the light is not necessarily coming from the left, it is coming, in this case, coming from here, 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 in all directions. In a particular situation, it may be coming from the right. The light can come from any side, but when we have to solve problems regarding the reflection or refraction from spherical surfaces, we assume that light comes from left. So, if we draw a ray diagram, in that ray diagram the light will always be coming from the left, and then distances in the direction of light would be positive, against the direction of light would be negative. So, be careful, don't. I was asked this question several times by many students, sir, light is coming from all sides. I said the light is coming from all sides, but when you have to deal with problems of reflection or refraction from spherical surfaces, we assume that light is coming from the left, just to be able to apply Cartesian convention. Another thing that we assume, that the rays are near the axis. They may be parallel, they may not be parallel, but the rays are coming near the axis, in the vicinity of the axis, not far from the axis. These rays which are near the axis, they are called paraxial rays. And why are they important? Here I am not assuming that the rays are coming near the axis. So, I have taken this larger mirror for reflection, and the rays are coming from even larger distances, and you can see these rays, they meet at this point after reflection. So, you can see that these rays meet at this point. So, they do not meet at the same point after reflection, and this is what is known as spherical aberration. That is, there is no fixed point at which the reflected rays meet. But if we make the assumption of paraxial rays, then we can assume that they all meet at a fixed point, and that point we shall define as focus. All rays come to that point, but this is true only for paraxial rays. If the rays are not paraxial, they are far from the axis, then they can meet at this point, this point, this point, and so on. This is what is called spherical aberration. In the next lecture, we shall continue with this study of reflection and refraction from curved surfaces. We shall first define what are known as convex mirrors and what are known as concave mirrors. We shall define their focal lengths, and we shall see how the images are formed by concave mirrors, and we shall derive ultimately the mirror formula, which connects distance of the image, distance of the object, and the focal length of the mirror. We shall derive this formula, which is known as the mirror formula.